All right. That's how I make up finals. Yes. I'll turn on the camera in the office. You can watch me make it out. You'll have to have really good eyes. That's true. Anybody want to just go ahead and take this one? No, I mean right now. I mean you have 2 hours. Chickens. All right, having given away the easy final, shear at G. Nelson, how would you go about drawing the influence line for the shear at G?
I would make a cut at G so it have two different free-body diagrams.
Good.
And then would place a 1 unit load throughout the beam.
Probably where?
Just different points throughout the beam and solve the shear.
Oh, okay. There's nothing wrong with that. That'll work. In other words, you can put a 1 right here, and you can some moments about this point and solve for this reaction. Draw that as a free body. Knowing that reaction, you should be able to solve for the force then vertically at C. Knowing the vertical force at C, you should be able to come down here and cut it at G and solve for the shear, and that would be 1 point that you'd plot. You would plot the resulting answer at G at point A on your shear influence line. You are going to have to be real quick. You're going to be able to mess around with that method. Ruiz, how would you do it for the shear at G? I'd put a little kink in there. That's what I'd do. I'd take this piece right here home with me, and I would put it on the curb, and I would put a unit kink in it. And I would notice there's a pinhole here, and there's a pinhole here, and there's a pinhole there. And then I would bring it back on site, and I would hitch it up exactly as you see it right there. And I would be ready to let it go, and the guy would say, "Good Lord, don't let it go." I said, "Well, why not?" So it's going to fall down. It's just pinned on the left end, and there's just a chunk of steel sitting out in the air. Ease it down until these pins reconnect. And so holding this piece here, the thing rolls, and then when this pin goes here, then this pin goes here, and that's no good because now this pin doesn't connect, although this pin is connected. And therefore then I have to roll the piece up to get back to this piece of steel. This piece of steel is sticking out of the wall. It's pretty much rigid. And so then I find out what happens is that this pin goes to here. I'll do it with X's. And this pin goes to here. And I don't care how you get it back on those supports, but it has to be on those supports. And then the wiggly line is coming from home. The X's are after installation. And that's what I see. I see this pin put here, that pin put here. I had planned on putting this pin here first, but when it rolled down, these two pins won't go through those 2 points that are fixed. They don't move, so I had to drop the whole thing down to here. Now I'm ready to walk away, and my friend says, "Wait, wait, wait, you can't go yet." I said, "What's the matter now?" I tromped around on here, it stands up nicely. I jump up and down here, it stands nicely. I jump off this one, and then I notice this piece of steel hanging out in the air. Not acceptable. So I bring this pin down to here. And I insert the steel pin back in there. And there's your final influence line for the shear at G. Now that one is relatively short on the left-hand end, so it may very well be that your method where you were going to put a 1 here and 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 a 1 here might be just about as quick. I don't know. And if that's the only method you know, then that's the method you'll use, and that's certainly fine. Yes? Why did this piece get rotated? Are you talking about this piece? Why did it not get rotated? I was happy. I had fully intended to rotate it about this point. The only problem is when I rotated this thing right here, such that that moved down 1, this piece here moved down further than 1. And this guy still got to connect to the end of this cantilever beam. And so as I had done that, somebody said, well, that's no good. This pin right here is not in that hole right there. And I said, okay, I'm going to have to roll this piece back up to here. And so after I've done all that, what I notice is basically this pin went to the end of the cantilever beam, which is fixed. It won't move up and down. This one moved to this pin, which was fixed. It didn't move up and down. And this is a free body, and it's just a solid piece of steel, so it just moved down to there, which means this end here got moved down the number 1. All right. Moment at H. Let me redraw the original structure. That one's a little too messy to do much more with it. Same dimensions. The moment at H is desired. How would you solve for the influence line for the moment at H? Serrata? Serrata here? No? Oh, okay. Well, tell him I just gave away 10 points to everybody when he comes back. Leon? Have no idea at all? Not even the foggiest? How about a guess? 42? Roberts? Stick a 45-degree kink in it. That's what I'd do. Now, well, I don't mean to, to influence your decision, but here's the wiggly line, and there's the 45-degree kink. I mean, it's quite obvious that isn't going to fit. This thing came out of this socket in the wall right here, and I took it home and I kinked it at a 45-degree angle. Now, it's your job to bring it back on the job site. Yes, sir. If you always do your shear kinks this way, you come out with the right signs. So in other words, having kinked it up and to the right, your shear influence line gave you a positive area in this region and a negative area in this region. And if you'll check it out, what happens is if you put your vertical dead loads or your vertical live loads in this area, you get positive shear at point G. And so that's why we do it that way. You can certainly kink this one down and to the right. The only thing is if you do and then you put it all back together, it'll be upside down. In other words, areas above the line would contribute to negative shear by our sign convention for positive shear. And the same way with this. If you don't kink it down and to the right, when you put it all back together, it's upside down. It's the same numbers, same values, same everything. It's just you don't get positive answers once you put loads in positive regions, which is good enough reason right there to do it. Up and to the right and down and to the right when you kink it. All right. So now then all I got to do is get this little piece right here back right inside that little socket right there. And so I pick it up and I slide it in that socket, and now then I'll use X's. It comes straight out. So it comes straight out. Serrata, your friend has some bad news for you. He'll tell you in a minute. And at that point, it's kinked to the right. In other words, this, if you're looking this way, it's kinked to the left. And so I'm going to go down here at a 45-degree angle. Here I got something. I hate to use colors on things that you can't copy, but here's the influence line so far. And there is a pinhole right here, and there's a socket hole right here. And it's your job to connect everything up. And right now, this pinhole on this member doesn't agree with that pin at that point. So it's your job then to do that. And then it's your job to do that. And there's your influence line for the moment at H. Checking what all these numbers mean. When you bent this thing down and to the right, this dimension right here, how far it went down, since it's a 45 degree, it's the same as it went over. So that's 10 feet down. So when you put this thing back in this slot, since this goes over 8, that is a 45-degree bend. This goes down 8. From then on, it's merely similar triangles.
That part on the right should be like above the beam, isn't it? Like you just didn't draw it?
I don't know. You know, I make mistakes all the time, just not thinking and being careless. But what's wrong with this one now?
Oh, the part all the way on the right, it should be connected to that support, shouldn't it?
This support?
Yeah, shouldn't that?
It is, see. In other words, this is what it is when I took it home and it really wasn't connected to anything. And then when I brought it back and I went like this, bang, 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 it wouldn't go in there. And you said, well, no wonder it won't go in there. It's at a 45-degree angle. So what I had to do was I had to roll it down so that this piece of steel would go inside the old slot.
Oh, it has to go in horizontally, right?
Had to go in horizontally. So if this is now called horizontal, then the member is bent down and to the left 45 degrees. So once we get it in there, this is bent down and to the left 45 degrees.
So it always has to go in horizontally for the big supports, right?
Well, that's right. Yeah, it always has to fit back on the original supports as they're in the field before you took it all apart and took it home and hurt it. So is that okay now? That agrees, you're okay with this? All right. So now then if this is 8 and this is 10, then this green line right here has a slope of 8 to 10. 8 vertical every time you move 10. Since this dimension here is 8, it's not very well drawn to scale, but 8/10 is the slope, and therefore that's, oh, is it 16?
Yeah, it was 8 feet to point G.
Thank you. You're right. That is a 16 foot. I got too much junk up there. That is indeed. Well, I thought it was really badly shown. I didn't know why, but thank you. That is 16 feet. That makes a lot more sense. Still not very well to scale, but better than it was. So this is 16 feet across here. There's an 8 and an 8. So if this is 8/10 slope, then 8 is to 10 as question mark is to 16. 8 is to 10 as question mark is to 16. And therefore, question mark is equal to 16/10 of 8. Whatever that is. Somebody got a calculator? Getman?
No, I have a.
You have a phone? Can you text message somebody with a calculator?
Sure.
No? Okay, well, I'll just ask until somebody comes up with a calculator here. Booth? What do you mean, well, sir? How much? Thank you very much. 12.8. Incidentally, I forget who it was, and they probably don't come but every now and then. But I remember somebody in here giving me a right answer to something, and I said, tell me, and I'll put 1 point on your quiz. And was that you? Lie. Well, how come you didn't write that on your quiz? Well, okay, you need to give me that back. Or just give me a piece of paper with plus whatever I told you. I hate to, make these promises and then not do it. You wouldn't even give me an answer to the number. I had to get it from that guy over there. All right, 12.8 is to 4 as question mark is to 6. So that'll be 1.5 as big. And so that'll be 12.8 and 6.4, 19.2. So there's nothing to it. Well, there's nothing to any of this stuff, really, especially if you've been practicing with it. Here is your region that you would put if I ask you for negative moment. You'd cover up this area if you could. If I asked you for negative moment, you would put live load in those regions. For dead load, you'd put it all the way across because you don't get to selectively choose where to put your dead load. You now have 20 points. Halfway there. Huh? What is the influence line shown for? Shear, good. Shear at this point right here. What did the original structure look like? Well, I'd say the original structure had a hinge. That you're absolutely right. There's a hinge right there because otherwise it wouldn't have that kink in it. Had a support right here. Good. Wasn't a wall on that end because it's just hanging out. And there was a hinge at this point, and that's what the original structure. Something wrong with that.
You're missing a pin.
I.
To the right of the point 2.
All right. Very good. Put a pin here. Put a pin here. Put a pin here. I know something's wrong with that. Why? Falls down. And so you're right. There's the third pin. Roller. There's the original structure. Yes, sir.
What if we had taken that pin at one, what if we taken that out and it's just been solid right there?
If you took this hinge out,
Yeah, that hinge.
that'd be fine. I would be happy to give you that problem on a quiz, but it would have to be a different problem. The problem then would be draw the influence line for the structure shown. How about we say moment now at this point?
Well, I was just wondering if you did the shear at the same point and you took out that hinge.
Okay, shear at the same point. That's as good a question. Nothing wrong with that. Taking that hinge out, it's a new problem. And I'm now going to ask you for influence line for the shear at A, B, at C. I do the same thing as always. I take it home and I put a unit kink in it. And I bring it back and I put it on the structure. There's a pinhole here, there's a pinhole here, and there's a pinhole here. And so first I start off with the structure suggested as follows. Beep, put the pin in there. Let this thing stand like this and see how we like it. I don't like it. Falls down. Got a big old solid piece of steel hinged in one place. So I see a pinhole there, and I see a pinhole there. I'm going to roll the thing clockwise until that pinhole fits on that point. And I'm going to insert the pin. That rolls down one. So we didn't have any dimensions on the original structure, so let's just put some on here. 10 feet, 16 feet, 14 feet, 14 feet, 5 feet. I don't like 5 feet, 7 feet. All right. Now, where this thing is 16 feet long, it's going to roll down 1. This point, on the other hand, is not going to roll down a full 1 because it's not as far from the rolling point. So this now looks kind of like this. If it wasn't for that pin there, I could actually probably get you some values, some quantitative, real number values to 10 decimals of accuracy. But now then I notice that this pinhole needs to go here. And now then about all I can do is give you what they call qualitative kind of numbers. Probably can still use the influence line to tell the computer program where to put the live loads and the dead loads. So what I'm going to do is I'm going to go get a hydraulic jack and I'm going to press this point up to there and put the pin in there. As I start doing that, this pushes up to here. Okay. No, there are no hinges. We took the hinge out, was the request. Now, if there was a hinge, we'd be back to this. And so now I'm going to go ahead and I'm going to push it up to there. And as I do so, I'm going to be cranking counterclockwise on joint D, which is going to move this point down. And that point slightly up. So my final opinion of where the influence line goes for the statically indeterminate structure.
Yeah, it's supposed to be straight from
BC is slightly curved because you pushed up, and this guy, when you pushed up, he would like to go down, but this didn't let him. So that's got a little curve in it. Now, if someone was talking about AB, that is not curved. In other words, it's just like a paper clip. You're holding it here, but this free end of the paper clip is sticking out, and that free end of the paper clip is sticking out. Not that I would fuss at you if you did this. You know, I would say, well, maybe I'll get him a few points someplace down the road, and I'll try and remember that. You know, but I'm not sure that makes that much difference. I know right now where to put the load for this statically indeterminate structure. I would put the live load in this region for positive shear at this point. I'd put the live load between C and D, and I'd put the live load between E and F. And I'd put dead load across the whole thing. In other words, when I ran Matran, I would tell him, here's the original structure. My boss has asked me personally to find the maximum shear at that point. I would tell the computer program to put 2 kips per foot across the entire structure. That would be the dead load. And I would tell him to put 8 kips per foot across there, 8 kips per foot across there, and 8 kips per foot across there to cause the maximum positive shear at that point in the beam. And then I would hand that design number to the designer and say, when you pick out this wide flange, you make sure that this point has a web that's thick enough to handle that shear. And then for negative shear, I would put the loads from B to C and from D to E.
So the reason it's curved between B and C is because you kind of have to, like, get it up from D to E?
It's right. In other words, when you pried this thing up with great force from the hydraulic jack, this guy here wasn't allowing this point to roll down like he wanted to about point D. So this is actually bent like that. Then it kind of comes up like that, and it's bent like that. Yes, sir.
In the original problem,
Yes, sir.
you have that 6 feet dimension there?
That's right. I had to give you one dimension just to get started. See, because if I didn't give you at least one dimension, you could say, well, I think that's a 12. And then your structure would have been twice as long as I had intended. So that's why I gave you the 6 feet. And from that, you could calculate all the remaining lengths.
I tried to do that, and I didn't figure out how to,
Maybe we got that wrong.
well, how to get the links on the right side of the pin.
On the right side of this pin,
Yeah, because you don't know what the slope of that is.
I think you're right. It looked about 14 to me. No, I think you're right as rain, because it's not drawn to scale, and therefore it's very possible that this number right here, I think you're right, was 14.6. Then this number has to be 7.3. Is that right? I put an extra there, so I guess it was. But you're right. Somebody's going to have to give you another number here in order for you to determine what these are. And that wouldn't be right. I think I just picked a number there for some reason. I don't remember why. But this has to be, let's just say it is 14.6. This is 1 divided by 14.6 gives me the slope of this line. 0.4 times that should give you how long it is here. So this is the 14.6, as 0.4 is the question mark. Now then our question mark is a horizontal dimension instead. But that's a good point. Absolutely, you can't tell what this is just by looking at it. Yes, sir.
On the roller on the very right.
This one?
And so it didn't fall down, it doesn't matter.
This one here? No, a roller is okay. Well, see, that hinge will take axial force. That's just a structural shorthand. It really is made like this. Here's the wide flange. The thing comes out here. They'll cut those flanges off short and put a pin right in here, and the other one will come across. And put a hinge in there. How they really do it, you want to know the truth, they just take a wide flange and they put a wide flange pretty close up against it, and they put a plate in here. And the bolts really don't produce enough moment. In other words, in a wide flange like this, almost all of the moment comes from the flanges. So you cut the continuity of the flanges between two members, the moment's gone. And so when you put this on there, there's not enough moment there to hardly talk about. All right, solve for the maximum shear for the structure shown, loaded with an HS-2044 truck. I could ask you for the moment at any point, and then you'd give me an influence line. Or I could ask you for the maximum moment, in which case you'd split the centroid of the group of wheels with the center line. What is a HS-2044 truck? What do the wheels look like? Two bigs and a small, okay. I've got to have what big and small means, and we got to have where they're located. Got that information for me?
Well, it's got some 44s and some 20s.
Yeah, but where? There is a table. What page is it on? I wrote it down because I knew I'd need it. What did I do with it? Here we go. Page.
The final will be open book, right? So
Oh no. You're supposed to memorize all this stuff. It is in the book. But I gotta, let me see where it is. I thought I wrote that page down. 481 sounds kind of far back. Nope, not 481. All right, it's here. Indeterminate structures, indeterminate beam slope deflection, live loads, railroad bridges, page 284. Bound to be somewhere right around there. Page 284. What does it say? Page 284.
For the truck?
For the whole thing. For all three tandems, or whatever they call them.
It's 8,000 and then
Okay, and good. They're spaced.
The first one's 14 feet.
That's a fixed.
Okay, and then the other one can be,
14 to 30. And since we're looking for maximum shear, where are you going to put the wheels? Close together or far apart? Okay, about half and half sounds like. All right, well, let's put one set of wheels as big as we can get them right next to the point where we're looking for the shear. That's a 32 kip load. And if I put the other wheel here, if he would let me, and the other wheel here, would I get more or less shear if I put them here, or if I move them as close as I can get them to the reaction? Close as possible. And therefore, that's where I'll put them. I'll put another 32 kips. And I'll put 8 kips. And I'll put them 14 feet. And if he'd let me put them if he said they might make a truck that's 2 feet between this one and this one, he'd make me put them 2 feet apart. But it is possible for him to get as small as another 14 feet. And then all I got to do is solve for the reaction, because a free body would show you that the reaction and the shear are the same right there at that point. And I have the maximum shear due to that set of wheels, due to that truck loading. What's another possibility if it was lane loading instead of the wheel loading? What would you put on there then? I'm not sure we covered that, but you can look at it and see. So uniform load of how much? Got a book? .64 kips per foot. Would you put it all the way across? For this structure, you would. And then you have a concentrated load. How much? You got a choice there, don't you? Well, I'm not really a choice in this case. Which one do you have to use? Your words were 18 kips for a moment, 26 kips for shear, 26 kips. Just that easy. Solve for the reaction at that point. That gives you the maximum shear due to what they call a lane loading. I take it nobody wants to see that cranked out. All right, I have the statically indeterminate structure shown. I have already selected the released structure or the primary structure. I have already selected the directions of the unknowns. There's an unknown axial force in the member. There's an unknown shear in the member. And there's an unknown bending moment in the member. And I've chosen those as the positive directions. I ask you to set up the solution. Delta 1 is equal to delta 1, 0, plus R plus R1 delta 1, 1, plus R2 delta 1, 2, plus R3 delta 1, 3 equals how much? 0. Delta 2 is equal to delta 2, 0, plus R sub 1 delta 2, 1, plus R sub 2 delta 2, 2, plus R sub 3 delta 212223. Delta 3 is equal to delta 30 plus R1 delta 31 plus R2 delta 2 the 31, thank you, 32 plus R3 delta 33 is equal to 0. How many of those would you have to calculate to really get the whole job done? I hear you counting. I feel your pain. Keep going. Tell me. All right. Well, that's what I'm looking for. That cuts your work about in half. Because delta sub 2, 1 is equal to delta sub 1, 2. Because this guy is found by putting a unit real load in the number 2 direction. And this guy is found by putting a unit load in the number 1 direction at the number 2 position. I'm not sure I got those words out right, but they're the same. You can't tell which one's a 1 and which one is the dummy load. And so it has to give you the same answer, and of course the theorem already told us that. And you got to get this one, and you got to get that one, and these 3 you don't have to do. Would I really ask you for all of them? Nah. Well, yeah. But only if I was, really trying to lower the whole grade. I'm not. So let's find delta 1, 0. Delta 1, 0. There's the released structure. Here are the real loads. We would call that M 1, 0. Or let's see, not in this class. What do we call that? P. The P loads and the Q loads. Very good. And I think we subscript it with a 0. And here are the moment diagrams on the tension side. Do that in pen. This will be the same. Fortunately, whoever decided on this didn't decide to cut that thing at the 10-foot mark, because then you'd have had all kinds of different shared moment diagrams. Those will both be the same. What is the magnitude of that one right there? 50? It could be. Let me take a look. It's 2 tall. It's 25 wide. No, just the load is 50 times 12.5. So this would be 2 kips per foot times 25 feet. And then I'll put the moment arm in a brace so you know it's a different kind of a number. This is the load, there's the moment arm, 12.5 feet. And someone said 625? Thank you. So now I got the moment diagram due to the real loads. Now if I've been asked to solve for delta 1, 0, I got half of what I need. Next thing I need is a unit load in the number 1 direction. The number 1 direction is left and right. Here's the structure. There's the 1. Here's the moment diagram on the tension side. This height was 80 feet. This was 25. Therefore, the moment right here is equal to 80. And delta 1, 0 is equal to the integral of, what's this guy's name? This guy's name is m due to the q load in the number 1 direction. The integral of m sub p 0, m sub q1. Volume integrals will tell you what that is, of course, over EI. Is one of these with one of these. This has no moment in it, so the parabola doesn't combine with anything. Rectangle with a triangle. Rectangle's on the left, triangle's on the right. Answer is minus something. That with that is a LAC over 3. Those of you who are still integrating this stuff, that's certainly okay. Your equation is 625 with no x in it. And that equation is x. You'll probably get an answer just about as soon as I will. Spread over 80 feet. In my case, it's a minus 80 feet. The height of one of these is 625. The height of the other one was 80. Divided by, that's not right, LAC over 3, it's LAC over 2. Did somebody notice that error? I mean, I don't mind if you didn't see the error or not, but did somebody got, is this LAC over 2? I think that's right. It's just like a 2x4 where you have a piece of wood and you cut half of it off and throw half away. LAC over 2. Bingo. Probably if I was a nice guy, the next thing I would ask you would be delta 1, 1. Why? Or if I ask you to solve for anything else, what would you solve for? Delta 1, 1. Why? Because you've already got the moment diagrams necessary. And it is a triangle with a triangle. And it's a plus. And I don't remember that one. Is LAC over 6? Who's got a volume integral? Don't tell me you think it's over 6. I did that. I think it's over 6. You see?
I was testing.
You were not. You were dumb, just like me. Thank you. LAC over 3. If they point in opposite ends, is that LAC over 6? That's what it is. Yes, sir.
You drew those both on the tension side, and then since they're on opposite sides, is that why you got a minus?
That's right. Incidentally, this is wrong. Why is this wrong? Yeah, this number. You need to be careful whenever you use symmetry, because when you use symmetry to make your life easy, you may forget that symmetry means there's two of them. See, and we combine this one with this one, that's this guy. Then we have another one with this guy. So what I have written down right here is this number right here. It's this deflection due to the real lobes. But this side also moves away, so it's times 2. And then, of course, this one would also be times 2 of them.
What if you were to cut that frame at one of the corners?
Nothing wrong with that. You get answers no matter what you do. But you don't get the advantage of symmetry then.
Yeah.
And I'm not sure how much.
Oh yeah, because then the other, the M sub B doesn't go into your equation.
That's right, it all goes. But see, that's not a bad thing. By putting all of this moment here in simply one piece of steel, this guy has nothing in it, so a lot of those numbers cancel out. So somebody may have tried that and said, you shouldn't tell them that's not good. It's really pretty good. So I don't know. All right, any questions on any of them? Pop quiz will be, I'll get you to do one of them before we go. When I hear the bell go off, I'll pick one. Better be ready to do it. Well, not yet. I hadn't told you which one. All right, set up the solution for the structure by slope deflection. How many unknowns are there on this structure by slope deflection or by a stiffness method? 3 is a good start. There's an unknown rotation at B. Phooey. Well, everybody came today anyway. There's an unknown rotation at C. There's an unknown rotation at D. And since this is a pin, there's an unknown rotation at E. Are there any unknown translations? Are there any points on the structure which might, excluding axial effects, might move to the right? CD, that's correct. So there is another unknown, delta at C, which is equal to delta at D if we exclude the axial compression of that member, which is probably almost 0. So you would start setting up your equations. You would stand at A and look towards B, and you would write an equation that says M sub near far, that's what we called it, M sub near far is equal to 2EI over L on 2 times theta on the near end plus theta on the far end plus 3. He used a little psi symbol where psi was delta near with respect to far divided by the length of the piece you're working with plus any fixed end moments you were to call the delta over L a positive number if the member appeared to roll which way? Clockwise. You were to call moments on the beam positive if they went which way on the beam? Clockwise. And you simply write one for each one. The moment from A to B is equal to 2EI over the length of that member, which is 30 feet. On to 2 times theta at A. What are you going to do with that? Good. Plus the theta at the far end, which will be theta B. Plus 3 times the delta of A with respect to B. What are you going to do with that? 0. And the reason is this point's not going to move to the right because it is supported, and you're assuming, and you're neglecting the axial compression, the axial shortening of this member. And this doesn't move to the right, so neither does B, so this number is 0. Plus, now then you have some fixed end members. What is the fixed end, fixed end moment? What is the fixed end moment for a uniformly loaded beam? And the book, in his zeal to be nice to you, even puts in the signs. How much? WL squared over 12, that's correct. And on this end, it is minus, thank you. And on this end, it's a plus WL squared over 12. And you're talking about the fixed end moment near far. That's from, darn, I just looked at it, page 476. And the moment on the near end is a negative WL squared over 12, minus 2 kips per foot, times the length of the member, 30 feet, squared over 12. And then you write one for M sub BA, and you write one for M sub BC, you write one for M sub CB. You just keep on using the thetas. As you get to member BC, this number won't be 0. It'll be an unknown deflection of end with respect to that end. Since this is assumed going to the right, which it looks like it has to do, that will be a positive delta over L. All right, I still need to see a bunch of you about changing your grade on the quizzes. I know you've been gone. I don't know if you've had time to look them over and come up with complaints. So Friday at least, I need to get those from you. If you didn't want to come to class when I returned the quizzes, you can follow me to my office, and I will verbally abuse you all the way. And
Pretty tricky. If we have some questions about
you get a little longer, but you know, get on it. Don't mess with it. Get your final. Take a look at it. See if you think I rooked you. Look at the solution online. Get all your ducks in a row. Don't come in and say, I don't see what's wrong with this, and then I show you. That poisons the well for any other questions.